Hello everybody and welcome back to our course. So far we ignored in our analysis that there's the opportunity to trade and exchange duplicates with others. So for example, I have duplicates that a friend still needs and my friend has duplicates that I can still paste into my album. And yeah, from a practical experience, we can say that this helps a lot actually to reduce the amount of stickers we need to purchase to complete our album. And yeah, in this session now we will include the possibility to trade and exchange duplicates in our code. And then we analyze why and how this is beneficial for everyone. And we call it fair trading or perfect pooling because we make some assumptions, which are kind of idealized assumptions. However, it is actually always a good idea to set up a generalized model. And from there we can always loosen some assumptions if we like. So what assumptions do we make? So first of all, we assume that a group of collectors form a pool. So the easiest case is two friends and everybody in the pool is buying the same amount of stickers. So for example, everybody is buying 800 stickers. And then the friends are putting all stickers together into a bucket, and all stickers that appear 2 times or even more times, actually both friends can paste into the album. And all stickers that appear only once, they actually have to split these up and everybody gets 50% of them. And in this sense, they can maximize the amount of stickers that both friends, or to be more precisely, the pool that they formed, can paste into the album. And this is actually our idea. So 2 or more persons form a perfect pool. Alright, so let's start coding, and of course we import NumPy and we start with a toy example and take only one simulation, and we assume that our album has the capacity of only 10 stickers and we buy 7 stickers, and for the time being we now assume that our pool is 1, so we have only one person, so there's no effect of trading or pooling, and we have the C till 42. And actually there's no surprise, so we know the code already. So first of all, we create 7 times 1 random integers. So we want to purchase 7 stickers and our pool consists of only one person, so 7 times 1. And then we sort the vector and let's see what we get here. So we get an array here with 7 stickers, 3, 4, 5, 7, 7, 8, 10, and we have apparently 6 unique stickers. And then we are making the 2 slices and checking whether the respective elements are equal or not. And then we take the sum over the Boolean array and add 1. And we have 6 unique stickers, so that's here repetition. And now we want to examine the case where we have 2 friends actually, and they form a perfect pool. So now both friends are buying 7 stickers, so in total 7 times 2 is 14 stickers. So now here we have the pool of our 14 stickers. And then by intuition maybe we form our 2 slices, but instead of having the first slice beginning from actually the second element at index position 1, we start at index position 2. And also in our second slice we end at index position -2. And then we can compare element-wise both slices. And finally we can calculate the amount of stickers that both friends can paste into our album, the sum of both friends. And maybe intuitively we do not add 1 but 2 because we have a pool of 2. And we get 11 stickers that actually both friends in total can paste into the album. So on average it's 5.5 stickers. And we can check if this is true. So we have here our bucket, and the 3, both friends can paste the 3, so we have 2. Then the 4 also both friends can paste into. We have in total 4 stickers, 5, 6, 7, 8, so the third 7 cannot be pasted. 9, 10, so the third and fourth 8 we cannot paste into our album. we have only once the 10, so only one of the friends can paste the 10 into his album. So in total, there are 11 stickers that both can paste into their album. And yeah, to calculate the average amount that one member of the pool can paste into the album, yeah, we have to divide here our total sum by 2. So because we have 2 friends in our pool. So on average, each friend can paste into the album 5.5 stickers. Yeah, and we already might get an intuition or a rule how it works in general. So we can actually try to replace here the 2 by the variable pool. Also here. And here. And here. And here. Also we add the amount of members in the pool. And we divide also by the amount of members in the pool. So let's try 3 peoples in the pool. So we are creating an even larger bucket of stickers, so 3 times 7, 21. And we make the slices. And in the end, our result is that each of the 3 persons in the pool can on average paste into the album 6 stickers. So far we had only one simulation, but yeah, we can generalize our model by introducing many simulations, and yeah, there's actually not much to do here. So we introduce simulations equals 10. We have a pool of 2 persons. And yeah, the only thing we have to change here, so initially we create 10 times 7 times 2 stickers that the whole pool will purchase, and then we reshape into 10 rows. So the 10 rows are for the simulations, and in each row there are 7 times 2 stickers. So in each row we have the pool of 14 stickers. And there we're getting a matrix, and we can sort it for each row. So we need to include here axis equals 1. And there we are getting the array, so we have 10 simulations, and we have 10 times the pool or the bucket of 14 stickers. And then again we can actually calculate the amount of stickers that each member of the pool can on average paste into its album. So let's check results. So in the first simulation, everybody can paste on average 5.5 stickers, in the second simulation 6.5, in the third simulation 6, and so on. Yeah, now we can move back to our sticker album challenge where we have our album capacity of 600. And in the function body we adopt the code that we arrived a few seconds ago here, and here in the function header we have to introduce the argument or the parameter pool. And by default we can set it to 1. So also we have the album capacity, purchase stickers, simulations 5000 as a default value, and we have the seed and the low percentile and the high percentile. And in the end we return the low percentile, the median and the high percentile. So let's run the cell here. And then we can call our new function with the added functionality that we can also simulate the exchange or trading of duplicates. And the case we already know is that we have a pool of 1 and the purchase stickers of 800. So we would expect to get here 442 as a median value. And now we can check the impact of having one friend that forms a perfect pool with us. So also we assume purchase stickers of 800, so both friends are purchasing 800 stickers. And let's see what we get. So here apparently we can increase our median value of unique stickers from 442 to 503 by having a friend which exchanges and trades duplicates with us. That's quite a tremendous effect actually. So we can increase the amount of unique stickers by actually 60. And we can even increase our pool. So let's assume we form a pool of 10 people. everybody's purchasing 800 stickers. And now our median is 581.5. So this is a great improvement actually. And yeah, you might have recognized that calling the function took us quite a lot of time here in the end, because here we formed a pool of 10 people and we actually needed to simulate the purchase of 10 times as much as stickers as we have here in our pool equals 1 case. So it's getting even more and more inefficient here and takes longer to calculate if we increase our pool. And the question is now, can we make our code or our function more efficient? At the very beginning of our course, we said that by increasing the amount of simulations, we can reduce the random noise or statistical noise. So by having a large amount of sims, say 5,000 or 10,000, our results we get, so our percentile or median, should be very reliable with very little impact of randomness. And what we can do now, actually, we can change here our seed and check how much of our result is actually influenced by randomness. So we set purchase stickers to 800 and we have a pool of 1 and we have 5,000 simulations. And we run the simulation here 20 times and 20 times with a different random seed. So let's do this. Yeah, and there you can see with 5,000 simulations, there's actually no variation at all. So in every case we get as a median 442, and for the low percentile there's also very little. Here's a difference, but only a small one, and also for the high percentile there's very low variation. So now by further increasing the amount of simulations to, let's say, 10,000, gives us not more benefit actually. So our results cannot get more precise. But what we can do, we can check if we can reduce the amount of simulations, and maybe we still get very reliable results. Yeah, and there you can see, so the variation increases as we reduce the amount of simulations. So depending on our purpose, it's still quite precise or not precise. So in this case, now I would say we should stick to 5,000 simulations if we have a pool of 1. So we have very little variation. And then we can make the same analysis for, let's say, a pool of 10. And we keep the simulations at 5,000. And let's run here. Yeah, we can already see that it's much slower, so actually 10 times slower here. But we already can see that the variation here is very low. So we can maybe reduce here the amount of simulations to 500. So we multiplied the pool by 10, and maybe we can reduce the simulations also by the factor 10. Let's see if we still have reliable results. Yeah, here in the median you can see it's only 0.1 or 0.2 difference here, and also in the percentiles not too much variation, so 500 should be a good idea with pool 10. So let's also check 50. Yeah, now the variation here is getting bigger, so maybe 500 should be okay. So let's check also a pool of 100 people with 500 simulations. Yeah, now we can see here we are actually too close to 600, and at 600 there's no variation anyway, so maybe we have to reduce our purchase stickers so we end up in the more moderate part of the curve. Let's say 550. Yeah, now we can see here with a pool of 100 people and 500 simulations, there's only very little variation here. So maybe then in this case we can further reduce the amount of simulations to 50. Yeah, and in the end, I think we get here a variation which is also acceptable. So with a pool of 100 people, we just need 50 simulations to have a reliable result. So maybe now we can generalize. So if we have a pool of only one guy, we need 5,000 simulations to have a reliable result. And once we increase our pool by the factor, say, 10, then we can reduce our amount of simulations by the factor 10. And also, if we increase our pool by the factor 100, we can reduce our simulations by the factor 100. And the reliability of our results stays high, and still we have a fast and efficient code. So now we have to change our function slightly. And we introduce here this line. And what the line actually does, it actually recalculates the simulations. In the function header here, we pass the amount of simulations of 5,000. And here we are recalculating the amount of sims depending on the size of the pool. And what we are actually doing, we are dividing the amount of simulations by the size of the pool. And then we round it to 0 digits because there cannot be fractions of simulations. And then we say, okay, at least we want to have 5 simulations. So we take NP max of here the rounded result and 5. So we have at least 5 simulations. So even if we have a pool of, let's say, 10,000 people at the very high end of the size of the pool, our code gets a little bit more inefficient, but that's okay. And then we transform here the number into an integer. Because for the simulations parameter, we have to make sure that we have an integer, not a float. And even if we round here, we do not transform our float into an integer. We only get a float with 0 digits. Alright, so let's redefine our function. Yeah, and then actually we can calculate, let's assume we have 600 stickers you want to purchase, and we have a pool of 100,000 people. Then we can calculate our results, so our percentiles and median. And I would expect actually to be very close to 600. Yeah, we've seen it took us a while, but not too long. And we see that we are very close to 600. And if we have, for example, a pool of only 10, then our code should be still very fast. Yeah. And also with 100, we should be very fast. Alright, so in this session we included the exchange or trade of duplicates in our code, and we only needed minor changes in our vectorized code. Before we had here a 1 and we replaced it by pool, and also here. And by doing this, we increased the functionality of our code tremendously, while the performance is still very high. And still we only need a few lines of code. However, the code might be less intuitive at a first glance and also at the second glance for others. And it also might be harder to come up with the solution. And in many cases, we need some trial and error steps to come up with a solution that works. And that's actually the drawback of a vectorized NumPy code. Alright, so this is it for the time being, and in the next session we will visualize our findings so it gets even clearer how to define an efficient strategy to minimize the amount of stickers we have to purchase to complete our album. So see you there. Bye.